All right, the next unit of material that we're going to cover is all about probability and statistics. And these things kind of build on each other. So in order to do certain kinds of statistics, specifically inferential statistics, all of inferential statistics is built up on probability models. And so you have to know about probability in order to be able to extrapolate from the data that you collect when you do statistics. And this is stuff that you would learn about in detail if you were to take a statistics course. We're just going to kind of scratch the surface and give some kind of basics here. So in order to do statistics, we have to know probability. In order to do probability, we have to know how to count things, which sounds really kind of silly. Of course you know how to count, right? But when I say that, what I mean is we have to know how to count abstractly, because sometimes there's going to be a lot of items, that we have to count up, and so we have to have a good way to count those things up kind of strategically, I guess. So that's what we're going to talk about for the next 3 lectures, is we're going to talk about counting techniques. And so to begin with, we'll start like right at the beginning with just basic counting, like you learned in kindergarten, right? So we'll talk about counting by just listing out the possibilities. And then later on in this lecture, we'll also talk about using tree diagrams to count, which, we've seen tree diagrams in this course before. But anyway, so for example, in how many ways can we do each of the following? So in how many ways can we flip a coin? Well, one way to answer that question would be to list out the possibilities when you flip a coin. And I'm going to use set notation to do that, right? So if I flip a coin, one possible outcome is that I flip heads, and the other possible outcome is that I flip tails, okay? So the number of ways that I can flip the coin is the cardinality, the cardinal number of this set, which would be 2, right? So there are 2 ways to flip a coin. So number of ways to flip a coin is 2, okay? How many ways can you roll a single die? So when you roll a die, which by the way is the singular form of dice, right? So when you roll a die, then there are 6 possible outcomes, right? The possible outcomes are you can roll a 1, or a 2, or a 3, 4, 5, or 6, right? So how many ways can you roll a die? 6, right? There are 6 possible outcomes. How many ways can you pick a card from a standard deck of cards? Well, here's a standard deck of cards for those of you who are unfamiliar with a deck of playing cards. Each deck of cards is split up into different symbols that we call suits. So we have hearts, clubs, diamonds, and spades. And then each of the suits have the same ranks. We call these things ranks. So ace is the same thing as 1, then 2 through 10, and then you have jack, queen, and king. And jack, queen, and king cards are called face cards. Anyway, but if you count up all of these cards, you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 times 1, 2, 3, 4. 13 times 4 is 52. So there are 52 ways that you could pick a card from a standard deck of cards. Okay? How many ways can you choose a features editor from a 5-person staff? Well, this one we can't really list out all the possibilities because we don't know the name of the names of the staff members, right? But if we knew their names, maybe we could call them person A, B, C, D, E, right? And then you could count up, okay, so there are 1, 2, 3, 4, 5 people in the staff to choose from. So obviously, if you're just choosing one features editor from that group of 5 people, then there are 5 possibilities, right? 5 possible outcomes. Okay, so obviously you don't have to like overthink these, right? They really are as simple as they seem. And on a test or a quiz or something, you wouldn't necessarily have to show any work here, right? You could just write down the answer because it's, they're all kind of obvious. But we're going to build up to more and more complicated types of counting. So let's look at another one. It says the Engineers Without Borders chapter on your campus is raising money to build to build and install a water purifier for an orphanage in Honduras. They are planning to have 2 major fundraisers, one in the fall semester and a different one in the spring. They are deciding among an online auction, air hockey tournament, themed road race, and karaoke night. In how many ways can the chapter select the fundraisers? Okay, so they're not going to have the same fundraiser twice, right? They're going to do one fundraiser in the fall and then a different fundraiser in the spring. And then these are the 4 options, right? They can do an online auction, they can do an air hockey tournament, they can do a themed road race, and they can do a karaoke night. So I'm just underlining the letters that I'm going to use to symbolize each one of these things, right? So let's list off the possibilities. Let's say that in the spring they decide to do the online auction. So in the spring they do the online auction, O for online auction. So then in the fall they can do either the air hockey tournament, the themed road race, or the karaoke night. So I'll say if they do the online auction in the spring, then they could do online auction in the spring and air hockey tournament in the fall. Or they could do the online auction in the spring and the themed road race in the fall. Or they could do the online auction in the spring and the karaoke night in the fall. Right? So those are all the possibilities. If they do the online auction in, I don't know if I was saying, I think I was saying that backwards, but whatever. If they do the online auction in the fall, then these are the options for what they could do in the spring. But they don't have to do the online auction in the fall. They could do the air hockey tournament in the fall, right? So it could be air hockey tournament in the fall. And then maybe in the spring they do the online auction. Or maybe they do air hockey tournament in the fall and the themed road race in the spring, right? Or they could do air hockey and karaoke. So I think you can see kind of how this is going, right? I'm just trying to list out all of the possible options. Okay, so those are our options. They could do the themed road race. So it might be themed road race and online auction, themed road race and air hockey tournament, or themed road race and karaoke night. And then finally, they might do karaoke night in the fall semester. And so if they do karaoke night in the fall semester, they could do online auction in the spring, or they could do air hockey tournament in the spring, or they could do themed road race in the spring. So those are all of the options, right? This is our set of possibilities. Okay. So in how many ways can the chapter select the fundraisers? Well, we've got 1, 2, 3 times 1, 2, 3, 4, so 12. All right, 12 different ways to choose the fundraisers. Okay. Now here, maybe I'll pause to say this because it depends on if we're counting OA to be different from AO, right? Or if we're counting AT to be different from TA. Because OA and AO, it's the same set of fundraisers, it's just a different order. So, if those count as 2 different things, then yeah, there are 12 different ways. If they count as the same thing, then I guess there would only be 1, 2, 3... only 6, right? Because we've double counted all of them because we've rearranged the orders. So it depends. I think maybe the problem could be worded a little bit more clearly so that you know whether or not the order matters in this particular problem. But that's something that we'll talk about in more detail a couple of lectures from now. But anyway, for now we'll just say 12 on this. Okay? So this is how you would count something up if you're just trying to list out all of the possibilities, and then you can count up the possibilities. What we're going to do now is practice using tree diagrams to help us count stuff. And this first example is one that we've seen before in this class. But it's in how many ways can 3 coins be flipped? Okay, and it doesn't matter, if these coins are all pennies or if one is a penny and one is a quarter or whatever. It doesn't matter, right? But we'll start with the first coin, right? So with the first coin, you can either flip heads or tails, right? So that's the first coin. So that's like our very first flip. Once you flipped that coin, now you're going to flip the second coin. And the second coin, you could end up with heads or tails, or you could end up with heads or tails here, right? And then for the third coin, each one of these options could result in heads or tails again, right? So if you flipped heads on the first one, heads on the second one, then on the third one you could flip heads again, or you could flip tails, right? If you flipped heads on the first one, tails on the second one, then on the third one you could flip heads, or you could flip tails. If you flip tails on the first one, heads on the second one, then you could flip heads or tails on the third one. And if you flip tails on the first one and tails on the second one, then you might flip heads on the third one, or you could just flip tails again, right? Now, the last column here in our tree diagram, this gives us the number of ways that the coins can be flipped, right? This first one represents the outcome heads, heads, heads. This second one represents the outcome heads, heads, tails, right? This third one represents heads, tails, heads, and so forth, right? Heads, tails, tails. This one is tails, heads, heads. Tails, heads, tails. Tails, tails, heads. And tails, tails, tails. Okay, those are all of the possible outcomes, number of ways that you can flip 3 coins. And you can see that they are all distinct. So what's the answer? 1, 2, 3, 4, 5, 6, 7, 8. So 8 is the answer. Okay, so tree diagrams, right, can come in handy for these kinds of counting problems. Let's look at another one. If we roll 2 dice, how many different pairs of numbers can appear on the upturned faces? Okay, so we roll 2 dice. How many different pairs of numbers can appear on the upturned faces? Well, when I roll the first die, there are 6 possibilities, right? I could roll a 1, 2, 3, 4, 5, or 6. Okay, so that's after rolling the first die. Okay, now, but I have to roll 2 dice, right? So when I roll the second die, if I rolled a 1 on the first die, the second die could be a 1, 2, 3, 4, 5, or 6. Same thing if I roll a 2 on the first die. If I roll a 2 on the first die, then the second die could again be a 1, 2, 3, 4, 5, or 6, right? I maybe should have done this the other way around. I'm not going to draw out the rest, but I think you can see kind of where this is going, right? This is going to lead to 6 different branches. 4, 5, 6. This one's going to lead to 6 branches. 1, 2, 3, 4, 5, and 6 maybe. This one's going to lead to 6. 1, 2, 3, 4, 5, and 6. And this one's going to lead to 6. 1, 2, 3, 4, 5, and 6. And if you notice, on the previous problem, the answer was 8. Well, if you look at how many branches our last column has, it has 1, 2, 3, 4, 5, 6, 7, 8. So it's really just the branches that matter, right? It's how many branches are in this last column. And so I'm not going to write out the numbers. I suppose you could if you wanted to write really small 1, 2, 3, 4, 5, 6 on all of these. But notice that this one corresponds to 1, 1. If I roll a 1, if both of the dice are 1. If this one corresponds to if I roll a 1 and then a 2, a 1 and then a 3, a 1 and then a 4, right? This one would be a 2 and a 2, a 2 and a 5, right? And so forth. Anyway, but if I count up the number of branches, I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36. So there are 36 possible outcomes. Okay, and you could list them all off if you wanted, right? So 36 because there are 36 branches in the last column of the tree diagram. Okay, now some of you may have been a little bit frustrated because you may have said, well, you don't need to count them all. You can just say, well, there were 6 possibilities on the first row, and then for each of those 6 possibilities, there's 6 more possibilities for the second row, so it's just 6 times 6, which is 36, and you're absolutely correct, but you're jumping ahead. We'll talk about that in more detail in the next lecture after this one, okay? For now, we'll just practice with these tree diagrams so that everyone can kind of build up their intuition to that level. Okay, next one. It says the promotions manager for the San Francisco Giants is planning some special event during an upcoming 3-game homestand. At each game, one of the Giants World Series MVPs will be honored. The manager has invited Edgar Renteria, Pablo Sandoval, and Madison Bumgarner to participate. In how many ways can these MVPs be scheduled? Okay, so the promotion, I'm going to read that again. The promotions manager for the San Francisco Giants is planning some special event during an upcoming 3-game homestand. So there's a 3-game homestand. Okay. At each game, one of the Giants World Series MVPs will be honored. Okay, the manager has invited these 3 people to participate. In how many ways can these MVPs be scheduled? Okay, so for the first game, there are 3 possibilities, right? They could choose Edgar first, or they could choose Pablo first, or they could choose Madison first. I should just write the first letter of their names. Okay, now if they choose Edgar on the first game, then there are only 2 choices left for the person to choose for the second game, right? So it's going to be either Pablo or Madison. If, on the other hand, they chose Pablo first, then there's only going to be 2 choices for the second game. That could be Edgar or Madison. And if they chose Madison first, then there's going to be only 2 choices for the second game, and it's going to be either Edgar or Pablo. Okay? So this is after the first game, this is after the second game. Now, by the time the third game comes around, there's only going to be one option, right? If they chose Edgar on the first game and Pablo on the second game, then on the third game, there's only one option. It's got to be Madison. If they chose Edgar on the first game and Madison on the second game, then on the third game, there's only one option. Got to be Pablo, right? If they chose Pablo first and then Edgar, then third has to come Madison. If they chose Pablo and Madison, then third has to come Edgar. If they have Madison and Edgar, then it has to be Pablo. And then Madison Pablo has to be Edgar. All right, so these are the different ways that they can schedule. And how many ways are there? Well, it's the number of branches here in our last column. That would be 1, 2, 3, 4, 5, 6. So 6 ways that they can be scheduled. And you could list them off, right? Edgar, Pablo, Madison, Edgar, Madison, Pablo, Pablo, Edgar, Madison, Pablo, Madison, Edgar, Madison, Edgar, Pablo, Madison, Pablo, Edgar. Right? So those are the possible ways that the MVPs could be scheduled. Right? So 6 possible ways that they could be scheduled. Okay. So you may notice that drawing these tree diagrams can be a little bit tedious. Fortunately, we can sometimes just visualize. Excuse me. We can sometimes just visualize the tree diagram in our heads without actually having to draw it. Okay? So let me give you an example of that and kind of talk you through my thought process. So imagine that you have 5 tops, 4 pairs of pants, and 3 jackets. How many different outfits are possible, right? Assuming that everything matches and blah, 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 right? How many different outfits are possible? Okay. So if I imagine the tree diagram in my head, I have 5 tops. So my first choice is going to have 5 branches coming off of it. Okay? Then I'm going to choose my pants next, right? There are 4 different pairs of pants. So for each top that I chose, I'm going to have 4 pairs of pants. So each of the 5 nodes at the end of this first set of branches is going to have 4 branches coming off of it because I've got 4 pairs of pants. So that's going to be 5 branches and then 4 branches coming off of each of those 5. So in total, that's going to be 4 plus 4 plus 4 plus 4 plus 4 plus 4. So it's going to be 4 5 times. So it's going to be 20 branches. So by the time I've made the choice of top and the choice of pants, I've already got 20 branches. Now, out of those 20 branches, I have to choose a jacket, and I have three possibilities. So each of these 20 branches, each of the 20 branches is then going to have 3 more branches coming off of it because I have 3 jackets that I could choose. So I'm going to have 3 branches times 20, right? I'm going to have 3 branches times 20 branches from the previous row. So that's going to be 60 branches. So how many different outfits are possible? 60. So if you wanted to, like, if you're just doing this in your head, then you could just say, what did we say? 60, right? Yeah, 60. But if you wanted to write something down to kind of remind yourself what we thought about when we were thinking through this problem, you could say something like this. You could say 5 branches for tops. Each of those has 4 branches coming off of it. For the pants, making 20 branches in total so far. Finally, we choose a jacket. So each of the 20 branches has 3 branches coming off of it, or branching off from it, you could say, coming off of it. Therefore, there will be 60 branches in total. So 60 is the answer. Okay? Now that's a lot to kind of write down, but again, the point of this is to try to visualize the tree rather than actually having to draw the tree, because as long as it took us to write this down, imagine how much longer it would have taken us to actually draw the figure, not to mention how much paper it would take to draw a tree diagram with 60 branches in the last row. So anyway, but there you go. Now, we don't always have to think in terms of tree diagrams. Another thing that we could do is to try to notice some kind of pattern instead. So here's an example of that. Consider the sequence of triangles in the figure below, which shows the beginning stages of a geometric construction called Sierpinski's triangle. So this thing is Sierpinski's triangle. And the way that it works is this. We begin with an equilateral triangle. That means that all of the sides are equal lengths. So that's stage 0. And then we divide that triangle into 4 parts, right, by drawing congruent equilateral triangles. All right, so we've split it into 1, 2, 3, 4 parts, and then we remove the middle one, and that's how we get to stage 1. And then we repeat this process on each of these smaller triangles to get to stage 2, right? So if I split this into 4 triangles, this into 4 triangles, this into 4 triangles, and then I remove the middle parts, then I get stage 2. And we could continue this, right? So I could split this into 4, 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 all of these into 4, and remove the middle ones to get the next stage. Okay, so this is how Sierpinski's triangle works. Sierpinski's triangle, by the way, is a fractal. If you've ever heard of fractals, like if you ever saw Jurassic Park, right? It's like a chaos theory type thing. Anyway, which we won't get into in this class, but it's an interesting thing. I might show you a video that relates to this idea. But anyway, the question is this: if we continued this process to stage 10, how many small green triangles would we have? Okay. Well, let's think through this. So, so I'm going to make a little table. So at stage 0, clearly we had 1 triangle, right? There was 1 green triangle. At stage 1, we had how many? 1, 2, 3 triangles. And at stage 2, we had 1, 2, 3, 4, 5, 6, 7, 8, 9. So notice that this is an exponential growth, right? To get from here to here, we multiplied by 3. To get from here to here, we're going to multiply by 3 again. So you could probably reason out that stage 3 is going to have 27 triangles because 9 times 3 is 27, right? And it also makes sense because in each case, you're splitting the triangle into 4 parts, but you're removing one of them. So it's like you split each triangle into 3 triangles. For each triangle, it becomes 3 triangles in the next stage. Okay? So stage 4 is going to have 27 times 3. That's 81 triangles. Okay, now here's another thing to notice. In order to get to stage 10, of course, you could go ahead and multiply times 3, times 3, times 3, times 3, a few more times until you get to stage 10. But here's another way to go about it, right? So we know that this is exponential growth. So we know that f of x has to be, and the exponential growth is times 3, right? Times 3, times 3, times 3. So we know that the exponential growth has to be of the form f of x equals k times 3 to the x, right? 3 because that's what we're multiplying by. If we want to find k, then we can plug in a number for x. 0 might be a good one, right? So f of 0, which by the way equals 1, that should be k times 3 to the 0 power. What's 3 to the 0 power? 3 to the 0 power is 1. So k times 3 to the 0 has to equal 1. 3 to the 0 is just 1. That means k has to equal 1. Okay, so f of x equals 1 times 3 to the x, or in other words, just 3 to the x. So now we can find f of 10, right? We can say, so at stage 10, we're going to have 3 to the 10th number of triangles. Okay? By the way, 3 to the 10th power is probably a very large number. Oh, it's not as big as I imagined. 59,049. Still, you wouldn't want to draw it, would you? That would be a lot of triangles to draw. Anyway, that's all I have to say about this section. So kind of a short section. I think the next section will also be a little bit on the short side too. So, but yeah, so that's that.